All right, so today we want to look at the method of variation of parameters, which is a $10 phrase to solve the D's that we've been solving, or actually the ones that we haven't been able to solve. I take that back. So our method right now was the method of undetermined coefficients, and remind yourself how that happens. So there's a couple of things at play. We solved this case first, equal to 0. That's known as the homogeneous case. And think about how we went about solving that. We wrote that as a characteristic equation, but we ultimately ended up with solutions to the characteristic equation that kind of fit this form. And then depending on what was going on when we solved that, whether we got two distinct roots, we created solutions. If we got a repeating root, that changed things. If I got an imaginary root, that further changed things. But I ended up with two solutions, some constant times each of those two solutions. Okay, so and we use that every single time. We use that for the equal to 0 case. We use this portion also in here for the method of undetermined coefficients. So with undetermined coefficients, we had some other function sitting over here, and that's what I started to say, is that keep in mind what's going on with that function. It had to be something like a polynomial, such that when I took derivatives, each one was getting simpler and would like something predictable was happening. It had to be something like a sine or a cosine. The derivatives of sine is cosine. The derivative of cosine is sine. And then it had to be like maybe an e to a power, because that, again, recurs over and over. So I can predict what that's going to look like. The things that I couldn't use the method of undetermined coefficients were things like maybe t to the negative 1. If this was t to the negative 1, each derivative gets more complicated, and it's impossible to account for all those different possibilities. Or something like a tangent. The derivative of a tangent is a tangent, and a derivative of tangent rather is secant squared. When I start differentiating secant squared, I end up with secants and tangents, and then I'm taking derivatives of each of those, and it just gets worse and worse as time goes on. So we want to look at another method, and I need to talk for just a minute about solving that method. So again, kind of think about where we've come with this. So what we're ultimately looking for is some function that's made up of the characteristic equation, which fits this form, and then solutions to the particular solution is what we called it, which is things that I solve from this form. And so that solution, big Y of t, may be have lots of pieces at play. It's got the characteristic equation and the particular solution. So thinking about that, I want to think today about creating this particular solution. So variation of parameters. I want to think about creating this particular solution so that it fits this form. Some function times y1 plus some other function times y2. And the only condition, and your book discusses this, but we're going to impose the condition v1 prime y1 plus v2 prime y2. I want that to be equal to 0. So let's kind of step through this particular solution kind of in the context of undetermined coefficients. Again, we're going to get to somewhere easy, I promise, so just stay with me for a moment. If that's y of p, then what does the particular solution, the first derivative of that, look like? This is a function, this is a function. That's product rule, right? So first derivative of the second plus the second derivative of the first. And the same thing with v2 and y2. First derivative of the second plus the second derivative of the first. But again, I can make use of this fact that y1 prime, v1 prime, all my subscripts and primes and double primes are running together. At any rate, the underlying portion, this thing and this thing, that's exactly what I got over here. So those stuff that's underlined becomes 0. So it happens that the first derivative looks like this. And then if I take the second derivative, again, several product rules going on. So let's see if we can sort through them. So I have first derivative of the second plus the second derivative of the first. And then the second product rule is first derivative of the second plus the second derivative of the first. Okay, and so I can't make use of this condition. I don't think that exists in that piece. But at any rate, we've got a function. We've got its first derivative. We've got its second derivative. So let's go back and use the idea of undetermined coefficients and plug it into this equation and see what happens, right? Remember, we were setting those things in y double prime, y prime, and y, and setting it equal to the function and finding our solution from there. So here we go. That equation looks like, at the top of the page, a times y double prime. So a times y double prime. So here we go. Let me just glance and be sure I've got my primes and double primes and subscripts and all correct. All right, so that's the first piece. So to that, I'm going to add b times y prime, which is b times all of this. And then finally, c times the function. Zoom out just here so you can see the whole thing. All right, and if you'll print the handout, you'll be able to see hopefully all of it at one time. But I end up with that whole thing equal to f of t, equal to some function. So let's see if we can find some places to make use of that identity. So I'm on the lookout for v1 prime times a y1. All right, so I'm going to hang on to several terms here. I'm going to hang on to this term and this term. And so those two terms that I've underlined in red look like a times v1 prime, y1 prime, plus I've lost the subscript again. That's why I was looking for just a moment. This would be a v2 prime right here. Sorry about that. And v2 prime, y2 prime. All right. So the other stuff that I think about is they're going to work out pretty nice. For instance, if I look at this term, and this term, things with V1s that are left in there, things with V1s. So those underlined blue terms, I'm going to factor that V1 out. And I'm left with a y double prime plus b y1 prime plus c y1. And then the same thing's going to happen with these v2 terms. So I'm left with, if I factor out the v2, let's see, let me write it in that same color. This is where I need my dry erase boards. So plus v2, and I'm left with an a y2 prime, double prime rather. I'm left with a b y2 prime, and I'm left with a c y2. And all of that is equal to f of t. All right, so notice what we've kind of created though. I have this portion, which is exactly what I've got in the original, and it's happened both times. It's just a y1 is being substituted in and a y2, but they satisfy the entire equation. So it happens that this piece is 0, and this piece is 0. So what I really end up with is an equation equal to f. So I end up, essentially, if I solve for this piece, I end up with two equations. So the first one is way back up here. This condition, that's the one that I'm going to use every single time. So, sorry, v1 prime y1 plus v2 prime y2 equal to 0. And then I'm going to manipulate this equation. If I divide through by a, then I end up with a second equation. So I have two equations, two unknowns, because I know y1 and y2. I know their derivatives, right? I found those from the characteristic equation. So essentially, I'm just looking for v1 prime and v2 prime. Two equations and two unknowns, so I just want to end up solving this system of equations. Now, keep in mind when you solve that system, and we're going to, of course, go through that. Took us a little time to get there, but that's okay. This is the meat. This is what we need. When I solve this system, I'm getting v1 prime and v2 prime. Keep in mind my particular solution, and a lot of students forget to do this, my particular solution is in terms of v1 and v2. So we'll need to do some integration there, and that catches a couple of students from time to time. So these are my equations. y1 and y2 come from the characteristic equation. F comes from whatever it's equal to. A comes from whatever number is sitting in front of y double prime from the form. So let's look at those right now. So here we go. Example 1. Let's take this equation, y double prime minus 2y plus y equal to t to the negative 1 e to the t. And again, this is one where the derivatives got more and more complicated. That didn't lend itself to the method of undetermined coefficients. So let me solve for the characteristic equation first. What's it going to be? R minus 1 times an R minus 1. So I get a repeating root of r equal to 1. So my two solutions are going to fall into the form of e to the t and t e to the t. And we had to modify those solutions whenever we got that repeating root. So solutions to the characteristic equation then is the sum of those, the linear combination of those. Okay. And when I think about y1 and y2, I'm really only interested, not interested in that constant. So I'm going to go ahead and omit that. We'll account for the constant down here in the characteristic equation. Okay, so let's use the method of variation of parameters. So again, y1 is e to the t. While I'm right there, let me go ahead and think about those derivatives. Y1 prime is e to the t. Y2 prime is going to be a product rule. So first derivative of the second plus the second derivative of the first. So we'll need all of that. So here we go. The method of variation of parameters follows this form. Equal to some function. All right, so for our purposes, the function is going to be whatever it's equal to way up here. And then I'm going to fill in for y1 and y2, y1 prime and y2 prime. I'm going to solve for v1 and v2. So I have v1 prime times y1, which is e to the t, plus v2 prime times y2, getting my derivative, which is t e to the t, all equal to 0. And then I'm going to fill into the second equation. Y1 prime is e to the t, and y2 prime is t e to the t plus e to the t. And I wanted that equal to the function, which is up at the very beginning, t to the negative 1, e to the t. Okay, so it's essentially a system of equations, and you can use whatever your favorite method is for solving that. Just looking ahead, maybe I'll just subtract one equation from the other. If I subtract here, those just cancel themselves out, right? I just need one to be negative as I'm doing that. So if I subtract, v1 e to the t minus v1 e to the t is 0. Here, I might want to write a little bit of that out. Let me get one other color. So I'm left with v2 prime t e to the t minus all of this. And I'm going to minus and subtract. So minus v2 prime t e to the t and minus v2 prime e to the t. And 0 minus this is a minus t to the negative 1 e to the t. So it looks like these two things go away, and there's a negative left on both sides. I think I'll just divide out that negative. And I think I can also just divide out e to the t. So it looks like v2 prime is equal to t to the negative 1, or 1 over t. So I'm interested in v2, not v2 prime. So if I integrate both sides, that just integrates into the natural log of t. So there's one solution. I'm going to circle it just so I can come back and find it. All right, I need to find the other solution. And I think the easiest thing to do maybe is just to plug into this equation where it's equal to 0. I can plug into any of them. I'm choosing to go back to the first. So here we are. Here's the first. Can you see that? Plus v2 prime. Well, v2 prime was t to the negative 1 times t e to the t, all equal to 0. So here the t's, t to the negative 1 and t ends up being just 1. They cancel themselves out. I can subtract e to the t to the other side and divide both sides by e to the t. And it looks like v1 prime is just -1, and if I integrate, v1 is just -t. So I'm finally ready, I think, to write my big solution to all of this. So again, my general solution is the characteristic plus the particular. So the characteristic equation is C1 e to the t plus C2 t e to the t, t to the t, plus the particular solution. The particular solution is going to be, fall into that format. I don't guess I wrote it up here, so I'll write it up here we can find it. V1 y1, V2 y2. So let's plug things into that. So here we go. V1 is -t times y1, which was e to the t. V2 is the natural log of t times y2, which is t e to the t. And sometimes, to be honest, the book does some funny things, some algebra, and taking out like terms and so forth to be able to get there. But at any rate, that's the solution to our first problem, example 1. And I'm going to have to stop the video because I'm going to be too long to upload, and so I'll make a second one with the second example.